talking about is kind of another preview of something that we are going to be taking a closer look at, actually second semester. So that's kind of what this unit is about, is just kind of introducing to you different things that we're going to be looking at more specifically with functions as we move through the course. So last class we previewed transformations, which is what we end this semester with. Today we're going to be previewing compositions and inverse functions. Both of these topics are something that's covered kind of in a general sense in Algebra 2. So we're going to kind of start going a little bit deeper into the things that we can do with those types of functions. Okay? So the first thing that we're going to talk about is a composite function. And a composite function is when two functions are connected to each other by the fact that the output of one is the input of the other. Yeah, you guys learned both compositions and inverses last year. We're just going to kind of take it to the next level.
So the thing I was learning with like the parabolas where you like move it, that was like my favorite thing last year.
Yeah, the transformations are fun, and we will get to those like in a lot more detail at the end of the semester. So we do a whole unit with transformations. Yeah, not like the unit. So for this first example, this says to find the cost C in dollars to paint an area A square feet, you need to know the number of gallons of paint required. Okay? So if I were painting a room in my house, like let's just say we have an open concept, what you want to call it. So we painted that a couple of years ago, and I left my husband the job of figuring out how much paint we needed, and he had to go to the hardware store, not one, not two, but 3 times, because he didn't have enough paint. So this is kind of a good example, because he got mad at himself, and I said, oh, you should have asked me.
Why do you not just do it if you do use your strong
Because sometimes I like to just let him do his thing, you know? Let him figure it out. It's fun to sit back and watch, right? So, and I hate painting, so I wanted nothing to do with painting that. Oh, no way. So, if we think about what this means, so if I want to know the total cost, I need to know how many gallons of paint that I need. And in order to know how many gallons of paint I need to know how much I'm painting. So there are kind of 2 things involved in finding that total cost. Okay? So if 1 gallon of paint covers 250 square feet, then the number of gallons that I need is going to be that total area that I'm painting divided by the 250 for each gallon. Does that make sense? Okay. And then my cost is going to be $30.50 times the number of gallons that I need. Does that equation make sense? Okay. So if I want to write a formula that just represents the cost, what I could say is, all right, well, the cost is a function of the number of gallons I need, right? So if I know the number of gallons, I'll know the cost. Well, in order to know the number of gallons I need, which is the input here, I need to know how much space I'm covering. So I've got this equation here. And I've got this equation here. So the number of gallons I need is a function of the area. So this would be an example of a composite function because the output of this function is n, and the input of this function is n. So the output of this function is the input of this one. And that's what it means for 2 functions to be compositions of each other. So if this function is represented by the equation a over 250, then I can take this and use it as my input here. So if my cost is $30.50 per gallon, so the cost is $30.50 times N, I can rewrite that as $30.50 times A over 250. Okay, so again, the input of this function is N, and the input here is the output here. Okay? And that's what it means for two functions to be inverses of each other. So in terms of some of the things that you will be looking at, so again, the function h is said to be the composition of functions f and g, so the two kind of put together. F is called the inside function. So I could have also rewritten this right here in function notation. So instead of using the input n, using f of a, so just using that equation, but the function notation. So this f of a part right here is said to be the inside function because it's in the parentheses. And then g is our outside function. Okay, that's what's on the outside. Okay. That's what's on the outside. So let's put this together in more of an algebraic sense by looking at this example right here. Okay, so two functions are given, f and g, 2x plus 1 and x squared minus 3. So the first example that we are going to look at is more of an evaluate example. So we will have a numerical answer here because we have a numerical input. So if I want to find f of g of 3, g of 3 is my input. Okay, because that's in the parentheses for f. So g of 3 is my input for f. So the first thing that I need to do is figure out what that's going to be. So I need to figure out what g of 3 is. So I go back up to the definitions of those functions. G of x is defined by x squared minus 3. So I'm going to take 3 squared minus 3, and I would get 6. 9 minus 3. So that is the output for g. So if I wanted to find f of g of 3, what I'm really wanting to do is find f of 6. Since that's what g of 3 is. Okay. So the output for g is the input for f. So when I figure out what that is, I go back up to the rule for f. It's 2x plus 1. So I'm going to do 2 times 6 plus 1, which is going to give me 13. So f of g of 3 would be 13. why don't you guys try the second one? So find G of f of 3. So don't do B yet, do the second part of A. Find G of f of 3. Why don't you just very quickly turn to the person next to you or across from you? Go through the answer.
Okay, I just did the 4, 6 times 8. I always say 48 instead of 49. I get this so confusing.
All right. So for this one, if we are finding G of f of 3, Natalie, what do I need to figure out first? I need to figure out f of 3. So f of 3, plug it into the rule. 2 times 3 is 6, plus 1 is 7. And then if I'm doing that, Kat, what do I do with the 7?
You take the 7 and plug it into u of x, which would be 7 squared minus 3.
Perfect. Which is 46. Very good. Okay. Does anybody have any questions about this part? All right, so now let's take a look at if I just want to find the formula. Okay, so we're still on this page, but now I'm doing the second part here. So for part A, I was just evaluating these two expressions, but now I want to find a formula for the composition, and this can sometimes be a little bit trickier for people to kind of see. So let's practice finding, actually we'll do this second one first because this one's a little bit harder. So let's find G of f of x. G of f of x. So if I'm wanting to do this means that f of x, that is my input for G. So what I'm really wanting to do is find G of 2x plus 1. Okay, f of x is defined by 2x plus 1. That is the input for G right here. Okay? So when I go to find a formula then, what I want to do, if this is my input, then that's what I'm substituting into my input for this function. So if G of x is x squared minus 3, G of 2x plus 1 is going to be 2x plus 1 squared minus 3. So I'm going to just simplify this, and that will give me my formula. So a couple of things to be careful of when you square a quantity. Remember that means that you are multiplying it by itself. So we're not just going to distribute the squared through, we're going to distribute everything. So when I do double distribution, this would be 2x times 2x, which is going to be 4x squared. That's going to be plus 2x, plus 2x again, plus 1, and then I've got that minus 3 on the outside as well. So after I combine like terms, my final formula would be 4x squared plus 4x minus 2. So I can combine the x's and I can combine the constants. This is a composition because this equation right here, 2x plus 1, that's the output for f and the input for g. So that's what gets plugged in to g of x, sorry. So why don't you guys find the other formula? You guys find f of g of x. So again, just turn to your partner or the others in your group. Kind of run through what you did. If you got stuck, now would be a good time to ask them for a little bit of guidance.
Negative 6. Oh, I got it. I put +1 twice. For the first one, I did the minus 3 and so the +1 and then the plus 1. It's the minus 3. It's supposed to be an equation on the other side. It's more like yeah, minus 3.
Okay. So if I'm finding f of g, so what I'm walking around, I notice most of you guys are totally understanding that means that g is going to be my input. So I'm just going to substitute that in there, but maybe not knowing what to do from there. So just think, if I asked you to evaluate, like these ones you guys had no problem with. If I say what's f of 3, everyone in this room knows, okay, plug 3 in for x here. Okay, I know that. So it's the exact same thing, except now we're not substituting in a number, we're substituting in an expression, another formula. So if I'm wanting to evaluate f of x squared minus 3, I'm going to substitute that in for x right here, and that would be 2 times x squared minus 3 plus 1. Okay. And from there, just be careful with your algebra. So 2x squared minus 6 plus 1 is going to give me 2x squared minus 5. Okay? I'll leave it up to you guys. Do you want to do one more practice like this really quick? No. Not over this. So just one more really quick. So turn your notes to the back. Yeah, to the blank. It's blank on the back. So make f of x 3x minus 5 and g of x negative 5x plus 1. We'll just do one of these. So why don't you guys find f of g? Okay, so you can work together, or if you want to try it by yourself and then compare, that's fine. Find f of g of x. Any other question cases? So composite is mean way. 1, 4 is 2. Number 2, if switch places. So I'm going to switch x and y. A lot easier to do. It's 3 halves. Work through it if you didn't.
What was 3 over 2?
All right, so all I'm really seeing here is maybe some algebra issues with the 2/3. So take it in 2 steps if you have to. So I know that to find the inverse, I have to switch my input and my output. So my outputs are y, right? So think about this in terms of the equation, not function notation. So if we switch x and y, that would be x equals 2/3 y plus 30. Okay, so if we work through this, Grace, what would I want to do first to get that y by itself again? Did you do that first? Subtract 30. And then you're absolutely right. We divide by 2/3, but let's take that in 2 steps to kind of show you what we're doing. So if this is 2 divided by 3, what undoes dividing by 3? Multiplying by 3. So if you do that first, just make sure you multiply that whole side by 30. Then the denominator cancels over here, and we'd have 3x minus 90 equals 2y. And now divide by the 2. Okay, so take that fraction in 2 steps if you have to. You could tackle it all here if you're a little bit better with fractions, but if not, there's no problem with taking it in 2 steps. So when I divide by 2, 3 divided by 2 is just going to be 3 divided by 2. And negative 90 divided by 2 would be negative 45. Okay. And then in function notation, since that's what it's asking for here, I'll just replace that y with the inverse of g. Okay. So that is one of the methods. And you usually do that just when you're finding inverses of equations that don't necessarily have a practical meaning in terms of representing something in the quote-unquote real world. Let me see if there's a good example in the book here. So the other method that we're going to talk about, so if you turn to the back just really quickly, I'm going to show you this example so you can see that on my desk. So one of the homework problems in your book, I don't even know if this is, I can't remember if this is one that's assigned to you. So if it is, then we're kind of go through it now. So number 38 says the daily cost of renting a car and driving up to 500 miles a day is given as C equals F of M equals 32 plus 0.19M. Okay, so that gives you the cost when you know the number of miles that you drove. Okay, so if you wanted to find the inverse of that function, okay, that equation has more of a practical meaning to it. It's not just the equation of a line or the equation of a parabola or something like that. The other way you can do it, finding the inverse, and this is what Emily said too. So if our equation is C equals 32 plus 0.19 m, again, this equation gives you the cost when you know the miles. To find the inverse of this, we could just take this equation, not change anything about it, but just solve for m. So right now, in this equation, C is my output and m is my input. So make it so that m is my output and C is my input. So we would take each side, subtract 32. So C minus 32 equals 0.19 m. And then divide by 0.19. I think that might be something kind of not so nice, so we might just want to leave it like that. Yeah, we'll just leave it like this. That way we don't have to round anything. So this would be an example of another inverse equation. Okay, because now my input is my output is m, my input is C. So usually you use this method when you're dealing with more contextual problems like this, as opposed to here's just an equation of a line or a parabola. So this gives you the number of miles when you know the cost. So for example, in a situation where you might want to use this equation instead, you could say, well, I have $200 to spend on this rental car. That's my maximum amount. I only have $200 for it. How many miles could I get from that? So I would want to use the inverse equation to figure that out because I know how much I have to spend. So I want that to be my input, so that I can get the number of miles as my output. Whereas if I say, all right, I know like if I had to rent a car to get from here to Chicago, I know I'm driving 200 miles to get to Chicago. How much is that going to cost me? So then I know the number of miles. I would want to use the original function to find the cost. Okay, so that's where the two different equations come in. Does that make sense? Okay, so like I said, it doesn't really matter to me which way you do it. Just make sure you're able to recognize both. Okay. All right, so let's look at a couple other contexts of using inverses, mainly graphing and tables, so lots of what we've already looked at for a lot of different situations this year. Really just practicing the notation. So we'll go through the graph together, and then I'll give you guys some time to look at the table here. So this first example, and this is the function that I'm using, if I wanted to find f of 0, right here is 0 my input or my output? It's my input. So I want to know when my input is 0, so right here, what's my output? And it would be 5. Nothing new so far. Now I get to this one. So this is saying what input has an output of 0. All right, so my output's going to be 0 right here. This isn't quite there yet, so I'm going to keep going until I see something that crosses, and I see that right here. So the input that has an output of 0 is negative 2. So this next one, here's something that looks a little bit different. So I see this inverse notation right there. So what this means, that 0 is usually where the input is. Right? Usually the quantity that's in the parentheses is the input. But since this is the inverse, that means that that's the output. So it's going to be negative 2 again. So now this is the inverse. So in that notation, that's now my output. So when my output is 0, I'm looking for my input, which is negative 2. So the same thing goes for this. I see that inverse notation right there. This value is normally my output. So if this is the inverse, that's my input. So when the input is 0, the output is 5. So these are kind of paired together, right? They're inverses because the input of one is the output of the other. Output of this one is the input of this one. Okay. So I see that these two are inverses, right? The input here, they're in different places. So when my input is negative 6, that's not the inverse notation. My output is negative 4. This is the inverse. So if this is usually my output, for the inverse, that's my input. And when the input is negative 6, the output is negative 4. So again, these are inverses. The input of one is the output of the other, and vice versa. Okay. All right, you guys work on using that notation with this table. All right, you guys know the drill. Compare answers really quickly. This one shouldn't take too long.
I know. So you don't have to take my quiz for me.
Darn, I was so looking forward to it. All right, let's run through these. We'll see if we disagree with any that anyone says, and we will move on if we are good. So, KD5 Coat, tell me what you got for f of 0. 2. Anyone have any issues with that? All right. Sarah, what did you get for the inverse of f of 0? 1. Anyone have any issues with that? No. Ella, what did you get for f of negative 2? 5. Any issues with that one? I agree. Olivia, what about the inverse of f of negative 3? 2. Any issues with that? No. Laura, what about this next one? The inverse of f of what is negative 3? That is undefined. Okay, if you can't figure it out on your table, that's what the answer is. Any issues with that one? Bree, what about the next one? That is negative 4. And then this last one, the inverse of f of negative 2. Nick, what'd you guys get for that one? Undefined as well. Okay. Does anybody have any questions about the notation from the graph or the table? This next part is what you guys overall need the most practice with, and that is when you are interpreting something. That is where I usually find taking points off most frequently on any sort of assessment that I'm grading. Okay, so what we're going to do is we're giving the meaning of the inverse of this function. Okay, so here's the original function. P is equal to f of t. Okay, this equation gives us the population in millions when we know the year. Based on the definition of the inverse is when the input and the output switch places. Okay? So if I were to write the inverse in function notation, it would be t equals f of p. So I don't want you guys to write anything on your papers right now. I just want you to take about 60 seconds to discuss what this equation would give you. All right. What did you guys say? What did you guys say for this one? Yeah. It gives you the year when the population is P million people. Okay? So you kind of want to follow this sentence structure. So this equation gives blank when the, and then whatever your input is, in this case it's population, is blank. So I would say this equation gives the year when the population is P million people.
So
Something along those lines.
like a function means like one input has one output.
Yes.
Or like multiple outputs.
Right.
Like what if you were the same like multiple outputs of a population? Like the population.
Oh, so then
is
the
constant.
inverse wouldn't actually be a function.
Okay.
That's what we would say. So if I asked you, like if I gave you a table for this scenario and I said, is the inverse a function? We would say yes or no, depending on if they repeated values. Does that make sense? So yes, if the population stayed constant, it wouldn't be a function because your outputs would give more than your inputs would give more than one output. Okay? All right, so again, start with this sentence structure and fill in the specifics from there. So why don't you guys talk about the next one too? The wording of this one's a little bit harder, I think. So if the original equation gives the number of inches of snow in the first T days of January, what would T equals F of N tell you? So talk about that really quick.
if the days of January when it has inches.
Remember, you should be able to give your explanation to someone that is not in this class, and they should be able to understand exactly what you are trying to say. So if you're just like, oh, that sounds okay, you probably need to clean it up a little bit more.
No, it doesn't make sense. The days. When it's like slightly warm.
I told you, did I not tell you guys that eventually it's going to switch?
Yeah, because it's been freezing lately, and now I'm just like,
Burning
up.
But I feel like during
So wear shorts in the winter and wear winter clothes in the summer.
What's going to happen? All right.
I figured it out.
So, what would this, almost done, what would this particular function give us? Jacob.
Gives 2 days of January when the snow is n number of inches.
I like that start, but I'm going to say that I don't think that's necessarily specific enough. Say it one more time. What did you say?
Gives T days of January when the snow is n number of inches.
Did you say something about how it's like the first T days? So it would be like, gives the first T days, yeah. The first T days when.
I don't even know if you guys. For example, January, the number of days. All right. So the last thing that we are going to talk about today is the domain and range of inverse functions. So this kind of ties everything together. Okay? Well, the definition of an inverse function is when your inputs and outputs switch places. Okay? So that means if two functions are inverses of each other, their domains and ranges also switch places. Okay, so the domain of the inverse is the range of the original and vice versa. However, they are not always necessarily going to be exactly the same depending on what kind of function you are looking at. So let's just take a look at 2a. We won't worry about doing b. So if this is my original function here, let's review the domain and range of this function. So if my equation is 1 over the square root of x minus 4, this is in the denominator of a fraction, so what can never be in the denominator? 0. And that quantity is under the radical. What can never be under a radical? Negative. So that means that my domain, if I wanted to figure that out, x minus 4 has to be greater than 0. It can't be negative and it can't equal 0. Okay? So the domain would be the inequality x is greater than 4. Now let's think about the range. So think about the outputs that this is going to produce. Okay? Because this is a square root, are my outputs ever going to be negative? No. Is my output ever going to be 0? No. So my range would be f of x is greater than 0. So if I want to write a formula for the inverse function, the domain and range should be very close to these two things switched. So the domain should be something very close to this. The range should be something very close to this. Okay, so let's figure out what the inverse is. So if this is my equation, I'm going to go ahead and switch x and y. So x is equal to 1 over the square root of y minus 4. So from here, we just have to be careful with the algebra. So what's one thing right now in this equation that's making this not look very fun? Square root. Okay, so let's get rid of it. What undoes square root? Square. You just have to make sure you square everything. So that's the mistake that I usually see with this. So if we're going to square this to undo it, we need to square the numerator and the left side. So every single thing needs to be squared. So my next step would be that x squared equals, and then 1 squared is 1. And now my radical's gone. All right, so that's one thing that's making this not fun because we're, again, needing to solve for y. So what's the other thing that's making this unpleasant right now? The fraction. Okay, so let's get rid of the fraction. What do we have to do to get rid of the fraction? Multiply the denominator by both sides. I'm going to leave it like this. Okay, I'm not going to distribute that through because I don't want two variables. I'm trying to get the y by itself, so right now the quantity that the y is in is being multiplied by x squared. So what undoes multiplying? Dividing. So now I have y squared, not y squared, y minus 4 equals 1 over x squared. And so now what do I have to do to get the y by itself? Add 4. Okay, so the inverse of this function, the inverse of f of x, is going to be 1 over x squared plus 4. Because I had to get the y by itself here, and this quantity that the y is in was being multiplied by x squared, so to undo multiplying, we have to divide it. So if I find the domain and range, which if you feel confident about what you did up here, you should always know, all right, might not be the exact same, but it should be pretty close. So if we look at this function, here's our inverse. The x is in the denominator of the fraction. What can ever be in the denominator of a fraction? 0, okay? But I can substitute in negatives, like I can have a negative fraction, that's okay. So this is an example where our domain's just a little bit different. The only thing that x can't be here is 0. But it's okay for x to be negative. I'm allowed to do that because it's not in the radical. I don't have a radical anymore. So I know the range should be something really close to what I had for the domain here. So let's think mathematically about this, and then we can look at the calculator if that doesn't make sense. So regardless of what I plug in here, am I ever going to get, so let's forget about the plus 4 for a second, is this 1 over x squared ever going to be negative? Why? Because of the squared. So even if I substitute in a negative value for x, it's going to turn out to be positive. Okay, so this is never going to be negative. Because there's a 1 in the numerator here, is this fraction ever going to be 0? No. So I'm never going to have any negative values, and I'm never going to have 0, but I'm taking this and shifting it 4 up. So my range is going to be that the inverse of f of x is going to be greater than 4. Okay. If you look at that on your graph, this is what that looks like. Okay, so you can kind of see here, nothing is below that point. It levels off right there. So my outputs